Hello, this is Magic 063, Differentiable Manifolds. I'm Kirill Mackenzie, and this is the fourth podcast to deal with differential forms. At the start, when we first considered differential forms, I defined them in terms of their effect on vector fields, and this is certainly an important way in which to work with them. But it's also important to be able to work with them as defined on tangent vectors, and we did that last time. This podcast is concerned with 3 or 4 different topics that rely on being able to work with differential forms in terms of their effect on tangent vectors rather than vector fields. So first of all, think of Rn and think of the actual k forms. K equals 0 and k equals 1 are pretty straightforward, so think of 2 or higher. The k forms are generated by all expressions here, wedge products of dx, where x is one of the coordinate functions on Rn, and the indices are in strictly increasing order. Now, if you think for a moment, this is actually very straightforward. If you have a repetition in a wedge product, and you might have any finite number of other terms in this wedge product, but as long as there's a repetition somewhere, the wedge product will be 0. So we don't need to consider repetitions. And if we have a wedge product where the coordinates are not in increasing order, then all we have to do is interchange them, introducing a minus sign to do so. So this list of forms is very easy to justify. We can multiply these by smooth functions, and we can add them up, and by so doing, we get all the k forms on Rn. And it follows that at each particular point of Rn, the vector space of all the k forms has dimension n choose k. And also, of course, if k is actually equal to n plus 1, then there's absolutely certain to be repetitions, and therefore such a form is 0. N plus 1 forms on an n manifold or an Rn, n plus 1 or higher, are all 0. The top case is n forms on Rn, and these are all scalar multiples, multiples by smooth functions on Rn of this one n form here, dx1, which dx2, all the way up in increasing order to dxn. And this is, if I plug in a string of vectors x1 up to xn, then what I'll get out is the n volume of the parallelepiped, which is spanned by the x's. And this is a signed volume. It could be negative or positive. If there are repetitions among the x, then of course it'll be 0. But assuming that the x's are linearly independent, then they form a basis for Rn. And if the n volume turns out to be positive, then we can say that the basis is positively oriented. And if the n volume turns out to be negative, we say that the basis is negatively oriented. And this links this n form on Rn to the crude and basic concept of orientation in Rn. So this form is sometimes called the volume form, it's sometimes called the determinant form. Probably volume form is the better terminology to stick with. So on an abstract manifold, something similar can sometimes be done and sometimes not. Here's the definition. An n-manifold is orientable if it possesses a never-zero n-form. And basically, a never-zero n-form will enable you to do, at least locally, what I've just described here on Rn. However, if you have something like the Möbius band, that's a two-dimensional manifold, and every two-form on the Möbius band has zeros. That's not an orientable manifold, and if you try to do things in terms of positively oriented bases in the tangent spaces, you'll run into trouble there again. So, going back to the definition, assuming that your manifold is orientable, two never-zero n-forms are said to be equivalent if there's a never-zero smooth function f such that omega 2 equals f times omega 1. And of course that's symmetric and it's reflexive and transitive. So it's an equivalence relation, and an orientation on M or of M is a choice of an equivalence class, one of the two equivalence classes of never-zero n-forms. If you're used to working with Riemannian metrics, you probably know that you can define a volume form in terms of the Riemannian metric. And if you're used to working with symplectic manifolds, say of dimension 2n, then you can use the symplectic form to define a volume form of order 2n on your symplectic manifold. So these are cases where there's a natural volume form, or at least the natural construction of the volume form, in terms of the structure you've given it, whether it's a metric or a symplectic form. But it's perfectly possible to consider orientation without any such auxiliary structure. Okay, we may be able to come back to this later, but for the moment, that's all I want to say about orientations. Here's another thing that really requires differential forms to be defined in terms of tangent vectors. This is pullbacks. Given a smooth map F from manifold 1 to manifold 2, we can take a differential form of any order on the target and pull it back to give a differential form of the same order on the domain. And the formula is very straightforward. Take omega on the target, take omega on the target, and the pullback, denoted F upper star omega, is defined like this. All I've done is map the x's from the domain to the target by using the tangent map to F. Okay. So that's very straightforward, and the checks that it's alternating and linear are very straightforward. So two formulas. Doing the second one first. The pullback of a wedge product is the wedge product of the pullbacks, and the exterior derivative of a pullback is the pullback of the exterior derivative. These are both very easy to prove, and I'll leave them to you as little exercises. They're used repeatedly and don't really need any more discussion. Following on from that, we can state the Poincare Lemma. This is a fundamental result, first of all in Dm cohomology, but secondly for any sort of work with differential forms. And it's often paraphrased as saying that a closed form is locally exact. So I don't think I've written this down, so let's do it now. Closed means that your form has exterior derivative 0. Exact means that your differential form is the exterior derivative of some k minus 1 form. and I'm pretty confident that you know these terms already anyway. So 121, that was the formula on the previous slide, that the pullback of an exterior derivative is the exterior derivative of the pullback. And so if we look at an open subset of a manifold M, say U, then taking the pullback across the inclusion is in effect restricting omega to U. It gives a form on U regarded as a submanifold of M. Submanifolds in general are in a later podcast, but we did already talk about open subsets as submanifolds. So here's equation 121 again. In this case, the exterior derivative of the restriction to U is the restriction to U of the exterior derivative. So here's the statement of the Poincare Lemma. Given a K form where K is greater than or equal to 1, and a contractible open subset, we'll come to that in a moment, a contractible open subset U of M, if we've got that d omega on U is equal to 0, then there exists an eta, a K minus 1 form on U, such that the restriction of omega to U is d eta. Okay, now contractible, if you know a bit of algebraic topology, homotopy theory, contractible means that there's a homotopy from U to a point, but in actual fact, for working with smooth manifolds, it's almost always sufficient just to have the Poincare lemma for open subsets that are diffeomorphic to Rn. So that's easy to arrange because Rn is diffeomorphic to any open ball in Rn, and by taking a chart around a point in a manifold, we can get we get first of all an open subset in Rn, then an open ball within it, and then a diffeomorphism to Rn. So that's very easily satisfied. I won't prove this. It's a nice thing to go through. The proof itself is not particularly relevant at this level. If you want to go into cohomology theory in some detail, then yes, certainly you should know the proof. But for actually working with differential forms of low degree, I think the statement will be enough for now. I'm going to go very quickly through a construction that's quite important in more advanced work, and the first step is the concept of a simple open cover. And the first thing to think about is that it's very easy to cover an arbitrary manifold M with open subsets that are contractible. In fact, we just talked about covering a manifold with open subsets that are diffeomorphic to Rn. And that's good enough. But a very much stronger result is true. Arbitrary smooth manifold, then M has open covers, U alpha, alpha in some index set at script A, such that first of all every U alpha is contractible, but further every non-empty intersection of U alphas is contractible. Such covers are called simple or good. Now, two proofs of this. One is by putting a Riemannian metric on M, which is something that can always be done thanks to paracompactness and Hausdorff, and then using the concept of convexity. That's nice. I think that was due to J.H.C. Whitehead. There's another purely, you might say, topological proof, which doesn't depend upon a Riemannian metric or anything, any additional structure. Due to Andre Weil, it's a intimidating piece of work, but it's nice to know that it exists. It is possible to prove the existence of simple open covers more or less with bare hands. At least if you're Andre Weil, it's possible. So here's what I want to do. This will be quite quick, two slides, and at the end I'll explain why it's interesting. Start off with the closed 2 form. I've got an arbitrary manifold and I've got a closed 2 form on it. So d omega equals 0. Then I take a simple open cover. I should have said that. So each U alpha is contractible, or let's just assume it's diffeomorphic to Rn. And therefore I can write the restriction of omega as d lambda A, where lambda alpha, rather not A, lambda alpha is a 1 form on U alpha. Okay, anybody can do that. Now, consider the twofold intersections, the ones that are not empty, U alpha beta not empty. Restrict lambda alpha to U alpha beta and restrict lambda beta. Then you can take their difference on U alpha beta, you can take the exterior derivative, and what you'll get is omega minus omega on the restrictions, in other words 0. So lambda beta minus lambda alpha is closed on U alpha beta. So there are functions, that's 0 forms, f alpha beta, such that lambda beta minus lambda alpha is equal to d of f alpha beta. Now consider non-empty triple intersections. Restrict the f alpha beta and f beta gamma and f gamma alpha to the triple intersection, and then look at d of this. And I'm being a little bit casual with notation, but you can do this more precisely if you like. You get lambda beta minus lambda alpha, and then minus lambda gamma minus lambda alpha, and then plus lambda gamma, minus lambda beta. And the end result is 0, all those things cancel. So finally, that function, this thing here, is a constant on U alpha beta. And I'll write E alpha beta gamma for that constant. It's a real number. So I've started with the 2 form, closed 2 form, and I've converted it into a collection of real numbers indexed by triples of the open cover. And in fact, one can prove something about these E's as well. This is the crucial part of showing that if you start off with a de Rham cohomology class, a 2 of degree 2, then you can convert it into a collection of these things here. And they define what is called a Czech cohomology class. This is Czech in the name, in the sense of Eduard Czech, who was the man who proved that pi3 of S2 is not 0. This is a crucial construction in bundle theory. It was used in the 70s by Kirillov and Constant and I think some other people to give what's known as geometric pre-quantization. And in their work, the closed 2 form that you start off with here is indeed a symplectic form on M. And the question that they wanted to answer was, is that actually the curvature form for a connection in a certain principal bundle built on M? And these numbers here are the crucial, or I should say it's one of the crucial ways of determining when that is possible and when it's not possible. When it is possible, you get a vector bundle. You can look at the sections of that vector bundle. You can put an inner product on it. You can complete it to get a Hilbert space, and you can use that for your quantization theory. So that's a quite an old piece of mathematics, and of course quantization has gone a long way since work of Kontsevich and other people, but geometric pre-quantization is still interesting, and this actual argument that I've gone through is important for bundle theory in general, because bundles and connections can be done basically in three different ways. They can be done in terms of curvature, connection forms and curvature, and those are things that live in Dm cohomology. Or they can be done in terms of path lifting and holonomy, and those are things that live in singular cohomology. Or they can be done in terms of charts and transition functions and things like these E, alpha, beta, gamma here, and they live in check cohomology. And the fact that these three cohomology theories are equivalent and that you can pass back and forth between them in dealing with specific elements rather than just the classes is an important geometrically. Okay, I'll stop there. Now, I want to talk about differential forms of low degree on R2 and R3. This is very classical material. It's essentially advanced calculus, but I think it's useful to go through this fairly briefly. First of all, look at R2. So there are 0 forms, and there are 1 forms, and there are 2 forms, but that's all. Take a 1 form, first of all, omega. I can write it as p dx plus q dy. P and q are smooth functions, both of x and y. And to work out d omega, d, of course, preserves addition, so it's d of p dx plus d of q dy, and d of p dx is dp wedge dx, and d of q dy is dq wedge dy. And now we have this standard formula for dp, and so when I wedge it with dx, the first term drops out, and I just have partial p, partial y, dy dx. With dq wedge dy, it's the same argument, and I end up with partial q, partial x, dx dy. So the whole thing, d omega, is equal to this sort of cross difference of the partials times dx wedge dy. And d omega is actually 0, is equivalent to partial q, partial x equals partial p, partial y. And as I'm sure you know, this is the criterion for the existence of a potential function for omega, that is for the existence of a function f of x and y, such that partial f, partial x equals p, and partial f, partial y equals q. That's precisely the statement that df equals omega. So the Cartan calculus in this case amounts essentially to the well-known fact that if you've got a closed one form on the whole of R2, then it comes from a potential. If you're not on the whole of R2, if you've got a punctured plane or something more complicated, then of course that might not be contractible, it might not be diffeomorphic to R2, and you may only be able to do this locally. I'm sure you've seen that sort of situation also. Okay, Let's go on to R3 and look at the corresponding thing for one forms. Again, omega is a one form, and I'll write it as f dx plus g dy plus h dz, where the f and the g and the h are functions of x, y, and z, smooth functions. Then the omega comes out like this, and this is essentially just the same calculation as in R2, except that we now have three coordinates. And this should obviously remind you of the curl of a vector field. And that's a legitimate mental association to have. But I'm doing this basically to emphasize that what we have here is actually a differential form. We start off with a one form omega. We end up with a two form d omega. And it certainly looks like the curl of a vector field, but differential forms are not vector fields. So let's just hold that idea in mind and go on a bit further. I can say at the moment that the process of calculating d omega is transmogrified, can be transmogrified into an operator on vector fields that sends vector fields to vector fields. And that depends on using the inner product on R3, or you can think of that as a particular case of a Riemannian metric. But this is a genuinely new piece of serious mathematics that translates the omega and the d omega into vector fields and turns this process into taking the curl. Here's the next ingredient on R3. Take a two form, call it alpha, and write it as alpha 1 dy dz. So the one is going with the second and third coordinate functions, alpha 2 dz dx and alpha 3 dx dy. Then d alpha comes out like this, and by all means do this calculation. So this should remind you of the divergence of a vector field. And again, the same process of converting differential forms into vector fields enables you to think of this coefficient here as a function which is the divergence of the vector field that corresponds to alpha. And then you remember that the divergence of the curl of a vector field is 0. And that corresponds to d of d omega equals 0 for omega a one form. And the local existence of a vector potential, if your vector field has 0 divergence, that's to say it's solenoidal, then this corresponds to the Poincare lemma for two forms on R3. So the process of doing div, curl, and grad on R3, and to some extent on a Riemannian manifold, is covered just about everywhere. But what I've aimed to set out here is the original version of this, the purely abstract version that's independent of a metric, or for that matter a symplectic structure, and is purely a process of working with the differential forms. Okay, that's the end of this podcast.